Hello and welcome to the Qubit Guy podcast, brought to you by Classiq, the quantum algorithm design company. My name is Yuval, and my guest today is Bob Sorensen, Senior VP at Hyperion Research. Bob and I talk about what performance improvements customers expect from quantum computers, the mistakes that quantum equipment vendors might be making, and much more. We hope you enjoyed this episode. Please let us know how we did by emailing hello@classiq.io. That's hello@classiq.io. Hello, Bob, and thanks for joining me today.
Hi, Yuval. How you doing? And thanks for inviting me to speak on your podcast today.
So who are you and what do you do?
Well, my name is Bob Sorensen. I'm kind of the chief quantum computing analyst at a research company called Hyperion Research. And just to give you a little bit of background of the company, this isn't an advertisement as much as it is an explanation of our pedigree. Hyperion Research and the small number of folks that work there are basically come out of the high performance computing sector. Most of us have at least 30, 35 years of experience in high performance computing. And that was the traditional kind of Cray architectures, the high performance systems, the things you see on the top 500 list of the most powerful HPCs in the world. Well, about 5 years or 6 years ago, we started to get a lot of questions from our customers. Now, remember, our customers are HPC vendors and HPC users, and they start to say, we're hearing interesting things about quantum computing. What are the potential challenges? What are some of the things that we need to be preparing for? Were the kind of questions we started to get. So we started looking at quantum, not from the sake of quantum, for its own, purposes, but how it's going to integrate itself into the overall advanced computing architecture, whether it be HPCs on-prem, whether it be, HPC in the cloud, or whether it be perhaps things like post-CMOS, post-Moore kinds of architectures, such as neurocomputing or DNA storage or something. So we looked at it as more of an aspect of advanced computing and try to figure out exactly how it would fit into the overall advanced computing capabilities. Can users think about using quantum computing to address some of their interesting and challenging workloads that right now are on their classical systems? What do vendors need to do to prepare, to think about, should they be offering products? Should they be partnering with quantum computing suppliers? How is the calculus of their particular product development stream going to change? And so Hyperion Research has more or less been involved in that journey, and we've really spent a lot of time establishing some very good relationships with a lot of quantum computing suppliers and happily end users around the world to try to add some sense of context here. Quantum computing is not an island. It exists as an advanced computing element. And the ability to kind of talk to users and suppliers across the advanced computing ecosystem and say, this is where quantum computing fits in, I think is a significant value added at this time. And the reason I say that is because there is so much hype and so much misinformation and so much confusion about what quantum computing can bring to the table that in essence, I view one of my major roles as being perhaps a voice of reason in what's going on out there to try to sort out some of the issues. And that's really why I'm here today. And that's really been my mission really for the last 5 years.
I'm curious what the answer is. So how does quantum computing fit in the high performance computing infrastructure?
Well, it's interesting because if we could turn back the clock on some of these, on some of the rhetoric, if you will, there's 2 points I'd really like to stress. The first one is, I wish we hadn't named it quantum computing. I wish we had called it quantum accelerators. Because really for the near term, and I think for perhaps the foreseeable future in terms of quantum computing, really what quantum computing brings to the table in the advanced computing over scheme is the ability to offer some very significant performance improvements on a very narrow range of applications. As I say at some of the end of my talks, no one will ever say, let me go check my quantum computer to see if I have any new email. It's not a general purpose replacement. I like to think of it, and I don't want to belabor the analogy too much, but I like to think of it as what happened to it, say, when GPUs came along. Very interesting use cases, but not a general purpose solution. They accelerate specific jobs. Artificial intelligence, machine learning, deep learning applications are a great example, but they're not the end all be all to solve all use cases for all users. But for certain applications, they offer significant performance gains. And that's really where I think quantum computing needs to be. So that's really the first case, the first issue I like to talk about. The second one is this dichotomy that I see in the sector right now, which is between what the quantum computing suppliers are thinking and what the quantum users are thinking, or potential users in many cases. And if you read the popular press, you'll see phrases like quantum advantage or quantum superiority. The idea that the quantum computing community, the research aspects specifically, are looking for applications that have this demonstrated supremacy. The idea that I have an application that I can only do on a quantum computer because if I run it on a classical system, it may take 15 billion years, where I can do it on a quantum system in, say, under an hour. Well, that's the supremacy issue. And that's the one that I think the sector is concentrating a bit too heavily on, mainly because that is a relatively far off goal, and one that frankly I think is laudable, but I don't see it as a main point, specifically because when I talk to users, remember, those are guys that are looking at this primarily as accelerators. And when I ask users, what kind of performance gains would you want out of a quantum accelerator to justify you putting one in the basement or logging onto a cloud system, we found that almost half said 50x. Give me 50x performance gain. They're not interested in quantum supremacy. They're interested in a performance boost of 50x. Some of them, a smaller number, say a quarter, if I remember correctly, said if you give me 10x, a single order of magnitude performance increase, I'm going to be really happy about that. And what that tells me is users, much more modest performance expectations. They're not looking for new applications that heretofore were intractable in classical systems. What they're looking for is about a 4 to 5 year leap forward in progress. Because if you look at 10x as an interesting, or excuse me, 50x as a performance number, that's where the classical world at the high end generally moves to. If you want a 50x performance gain, you wait about 4 to 5 years. That's all they're looking for. And that tells me they're not looking for, unheard of levels of performance. They're looking for a competitive advantage against their non-quantum counterparts, and they want to turn that into some kind of economic advantage. And so this dichotomy in sometimes between what the quantum computing suppliers, I think they've almost forgot sometimes who they should be selling to. They're too keyed up with internal competition. Who's got the most qubits? Who's got the biggest quantum volume? Who's approaching quantum supremacy? Where the users are just saying, give us more realistic performance enhancements, and we'll be very happy to write the checks for you guys.
But 10x or 50x performance could definitely be game changers. I mean, I remember speaking with Honda several years ago when they were doing car design. They were doing clay models and would take them 6 weeks to make a model and then get the executives and then ask for changes. And all of a sudden with 3D modeling and the virtual reality, they could do this cycle in a day, and therefore they could roll out new cars or more innovative cars in the market much faster. So wouldn't you say that 10x or 50x is a game changer, even if that's all quantum delivers?
That's the thing. That's all the users are interested in. I think a 50x leap is significant for almost, like I said, at least 50% of the end users right now. They would love to have that. And so, it's, as I said, it's dichotomy between some of the suppliers I talked to. And I talked to a company a couple days ago, and I won't mention their name, even though it was actually a press briefing. And their philosophy was, we're 10 years away, because until we hit 1 million qubits, we don't see the financial return. And so I said, there's a risk in terms of sitting on the sidelines for the next decade when there's so much interesting work to be done. But again, there's this perception that if you're not offering these unbelievably, imaginable speed up levels, that it's not worth playing. And I think that's, the users aren't expecting that. And I think that some of the companies that are out there working today to not only establish, I think 2 major things here. Why do I always say 2 things? Because I keep them both in my head at the same time. I'll never say 3 things. The first one being establishing a sense of progress. So if you look at roadmaps, and I would point to say IBM or Honeywell or Rigetti, some of the hardware vendors out there of note, if you will, they have already published roadmaps that say we may not be there yet, but we are demonstrating progress on a regular cadence. We're doing something that says we will get there eventually, and they're trying to build confidence in what the users are thinking. And to me, that confidence building measure is critical. The other thing those companies are doing is they are working more and more with end users to develop applications. It's one thing to come up with a quantum algorithm. It's another thing to take that algorithm and apply it to a use case in a specific vertical that matters. And that's really the next big step in quantum. I can develop an algorithm, I can develop a piece of software, sell a piece of hardware, but when I want to sit down with an oil and gas company and say, I have a really interesting way to optimize how you extract oil from one of your large fields through a discovery, so it's an optimal extraction technique, the most oil comes out at the least possible cost, that's when end users sit up and take notice. And moving from the abstract concept of algorithms to viable end use cases that are demonstrated are what some of the progressive companies in the quantum computing sector are doing today. They're not saying, look at our speed up. They're not saying, look at how many qubits we're having. They're saying, we're exploring how we can save a company X amount of dollars because we can optimize their logistics process. We can optimize the flow of materials through a factory to push steel out in a more effective way. They're optimizing things like how I can do risk assessments of portfolios in near real time. So if I have a portfolio of 1,000 instruments, investments, and one or two things happen to go sideways at some point, how can I quickly decide how that affects my overall portfolio risk exposure? And if I can do that on a quantum system effectively, that beats a classical system, it perhaps only by a factor of 10. Well, if I have to wait 1 hour for that data versus 10 hours, that means a lot to me as an investor. That's a demonstrated use case that drives continued interest in the technology. Because right now we're at a point where if you look at a lot of what's going on in quantum computing, the major funding still comes from venture capital organizations and from government programs. And those guys, certainly the venture capitalists, to a lesser extent the government programs, they like demonstrated progress. They want results. They want return on investment. Politicians can be just as fickle as VCs when it comes to money. And for those of us who are old enough to remember the AI winter in the late 80s, where we saw AI having huge promise, huge investment, difficulty in delivering results, and then it just went away. And that was the AI winter, freezing of all work. It took almost 20 years really for that sector to revitalize itself. And it took kind of new programming, new hardware paradigms, a bunch of issues there. There is a looming specter. I don't want to say it's a high probability event of a similar kind of winter in quantum. Too much investment, too much promise without near-term delivery could spell concerns for funding issues. I've talked to a number of companies and I asked them about the specter of quantum winter coming. And the best answer I got was from CEO who basically said, I'm not predicting if quantum winter will happen or not. Just be assured that I'm preparing for one if it does happen. So there is this need to demonstrate that this is a vibrant and growing sector with promise in order to keep investment and R&D funds available until it reaches a point where it's self-sustaining. Revenue drives research, which drives revenue, and so on. And that's what the sector is trying to push itself towards.
But let me take the other side of the evolution versus revolution argument. I mean, new technologies come in, and sometimes you don't know what they're going to be used for. I mean, when you think about the internet being invented for one application, and what is it being used today? You know, what our cell phones thought that they were going to do, and what are we doing today? If you think about a quantum computer, even with 500 qubits, you cannot simulate 500 qubits today. And because you cannot simulate those, it's really difficult to build algorithms that take advantage of those. But if in a couple of years you'll have 500 or 1,000 or more qubits, then who knows what kind of revolutionary algorithms will be available for those. And it is, if you believe the vendors, 2 years away.
The beauty of the sector right now is there's so much work going on at every level in the stack. You know, I see hardware innovation, and we call them modalities, different way to achieve the quantum phenomena. You have superconducting qubits, you have trapped ions, you have photonics, you have also neutral atoms. You have all sorts of interesting ways. They each have their own strengths and weaknesses, but the point is, it's a vital sector. Anybody who says they know exactly which is the winning modality right now, I view that with a certain amount of suspicion. We really don't know who's going to win yet, but there's vitality there. There's lots of enthusiasm, lots of research. And we see that across the stack. We see that in applications and algorithms and middleware. The idea that people are out there looking at quantum compilers, the fact that you can write a quantum program that sits high enough in abstraction that you can be a Python programmer and make some quantum computing calls and not really care about what happens at the quantum level. It's like the fact that most Python programmers couldn't really explain to you how a CMOS gate works in a transistor of an Intel processor. That's where we're moving. And that I think is the interesting part of this, is that the sector can move in parallel. So we can have applications development and new algorithms and in some sense, wait for the hardware to catch up with some of those ideas. But the point here that's interesting is that in the meantime, some interesting work can be done. People are looking at noise tolerant applications. Some of the frailties of quantum computing can be mitigated by mixing applications that say, I don't need a perfect answer. I just need a better answer. That's why optimization right now is such a buzzword in the quantum computing space, because I don't need to have the optimal traveling salesman solution. I just need to produce a solution that's perhaps marginally better than what a classical counterpart could do at any given point in time. So again, it's the idea of demonstrating progress as opposed to reaching a holy grail of, we can all sit back now because the quantum is going to do everything we ever hoped it would. It's going to be a journey, and it's going to take some time for all that to unfold. But the applications, the algorithms, the hardware, the software, it's all evolving almost in parallel. And to me, I find that to be a very promising aspect of all this.
When you advise companies about quantum computing, do you recommend they start from the cloud or on-prem? And is the answer different for a commercial organization versus a federal one?
The interesting thing that's a great question, because it's really difficult right now, because I'm a fan of, letting 1,000 flowers bloom. The idea of throwing your software on a cloud, say it be AWS or Google or Microsoft or something. If you've got a very interesting but somewhat complicated algorithm, I question, how can you demonstrate and differentiate your product if you are one of 450 different quantum options on, say, a cloud service provider? It's hard to differentiate. It's hard to stand out. So if I'm talking to a very small company, perhaps a handful of programmers and such, with an interesting idea, the first thing is, just throw it on the cloud. That has a low barrier to entry. You can put it up there. But if it's an interesting algorithm or requires a certain amount of education on the customer side, how do you differentiate? So doing it that way can be a problem. The issue of the sector consolidating right now is an interesting one. We're seeing more and more partnerships being formed. So you look at software companies tying up with hardware companies as a way to offer up a single unified solution that still doesn't require one single entity to be full stack. It's difficult to be full stack. You need a lot of resources. IBM is probably the most successful full stack company, but if you look at their R&D budget and their financial and technical wherewithal, they can support that phenomena. Not a lot of companies have the kind of breadth and depth of resources to do that. So in some sense, it's really more about making sure that you understand where you fit into the sector and examine all the options, and don't just pick one. I love the fact that, as I said, because the stack is somewhat mature right now, if I'm a software company, I don't have to say, do I want to be a Rigetti software company? Do I want to be a D-Wave company? Do I want to be a Honeywell company? I can write code that runs on all that hardware. So don't limit yourself to a single thread just yet, because the jury is still out. It's still out on modalities. It's still out on hardware. It's still out on architecture, and it's still out on corporate winners and losers. So be flexible, be broad-based, and look for opportunities where they arise.
And as we get closer to the end of our conversation today, what do you think is missing other than bigger hardware as you go from the 20, 30, 40 qubits of today to 1,000 qubits tomorrow? Where do you think the biggest improvement needs to happen?
To me, the two biggest improvements, and I'll go a little nerdy here. I'm an electrical engineer by training. The two big ones are scalability. I like that people can make qubits, but if you think about how a traditional system is made today, you don't have one honking big microprocessor. You have 100,000 of them, and you hook them together, scale it, you scale up to get this capability. Well, the issue in the classical world is if you've got 1 million processors or 1 million cores and 100,000 processors, they have to communicate with each other. And the network is what limits performance nowadays. It's not the processor itself. It's the ability for the processors to talk to each other. I'm not clear yet which particular modalities and which architectures scale better. So to me, we're not going to reach a single chip that has a 1 million qubits in it. We're probably going to have 1,000 qubit chip and 1,000 of them communicate with each other. That's going to be the architecture of choice in my mind. So you have to look at which modalities not offer the best single qubit, but offer the qubit modality that allows you to scale in an interesting way. Because if you've got 1,000 chips and they're all quantum, if you can't communicate effectively in the quantum realm and you have to drop down to the classical world to run communications, it's dead. You're dead in the water. That's a particular problem. The other one that I think is important is I/O. It's difficult to communicate with a quantum computer. So there's all sorts of instrumentation and control processors. That's all classical IT, but the architecture needs to support that. How can I talk to that quantum processor in a timely way, give it lots of instructions? Because, you know, the wonderful dichotomy of quantum computing is most of the time you don't want to touch it. You want to maintain that quantum goodness. So you don't want the outside environment impinging on it at all. Except when you do, when you want to get in and you want to shove data down there, you want it to do its quantum goodness, and then you want to get the data out. So half the time, or some percentage of the time, you want to leave it alone. The other half, you want to be all over it so you can communicate with it. I/O, I think, is another vexing problem, because right now it takes an awful lot of control lines to control every qubit. Now, you know, a typical transistor has billions of transistors, a typical microprocessor, an advanced one, billions of transistors, not billions of I/O lines. It'd be kind of strange to have a laptop that had that. The quantum world has to deal with the fact that you now have to figure out, how can I get complex signals into a qubit or a quantum processor without having too much onerous overhead in the I/O capabilities. So scalability and I/O, I think, are the next big technical challenges from a hardware perspective. Software perspective, demonstrated use cases. I'm waiting for the people to come along and say, we just saved X billion dollars this year because we figured out an optimization routine for loading cargo on an aircraft. And now we can do it more effectively in real time. And this just saved us X amount of dollars on flight delays and fuel costs and such. More demonstrated use cases that a budget director can bring to the C-suite and say, you don't want to hear about quantum. You want to hear about the fact that I just saved you $50 million this year. And that's from the corporate side, that's, I think, is the next step, the next trend that I'd like to see happen more often.
Excellent. So, Bob, how can people get in touch with you to learn more about your work?
Well, you know, Hyperion Research, you know, we do have a website, and you know, we're pretty out there, and my name is Bob Sorensen, and I'll spell the last name because it's always spelled wrong. It's Sorensen, the E at the end. So if you just type in B Sorensen at Hyperion Res, I'm there. And, you know, the interesting thing is, because this is such a new subject, I have this wonderful responsibility of not only, you know, doing things that, you know, keep the lights on in terms of payment, but also consulting and talking to people and just gathering information and such. So in many cases, all I like to do is just chat with folks to hear their hopes and their dreams and their fears, so I can present a more accurate portrayal of how the sector is unfolding. So it's really more about having conversations at this point than it is me selling, you know, a glossy brochure-driven, you know, document set at this point. So reach out, contact. I have a number of decks. I'm more than happy to, you know, answer questions and give presentations going down the road. But, you know, with that said, you know, something like this to me is just fascinating in terms of getting the word out. And I appreciate the invitation today, and the fact that you actually let me talk, I think, for over 20 minutes, which shows how absolutely patient you could be sometimes, Yuval.
Well, it was my pleasure having you today. Thanks very much for joining.
All right. Thank you.